Hello, I hope you all had a nice lunch. I certainly enjoyed it. We start the session on edge intelligence and computer vision. I would kindly ask you on your questions to say in the beginning on Slido if the question is for Michele or Stefan. It helps going through the question. And we start with our first speaker, Michele Mango, Dr. Mango. He's has a PhD in electrical engineering, and right now is a senior scientist at ETH and director of the Center for Project-Based Learning. And he would present us about edge intelligence sensing for predictive maintenance. So
thank you very much. And I'm sorry, I'm a bit limited with my mobility. So I will try to sit here. And so I would like also to thanks for the nice invitation to this conference. And it's my pleasure to present my talk that is going from edge intelligence sensing from predictive maintenance. And I'm trying also to cover a different topic of my group from self-sustaining node and robotics docs. So, and we will see why they are common, in my opinion, or at least for what we are doing in our research group. So as you know, and as you are here, there is, since several years, a huge trend of moving the reactive maintenance. So maintenance was always needed on machines, our watches, trains, cars. You see from the REACH program we are having today that are many use cases of maintenance. And we are moving for many reasons, many aspects, from industrial aspect, marketing aspect, research aspect in people that are coming from academia in a very hot topic. And also what we are usually thinking about intelligent maintenance, that some computer robot is taking care of looking after our devices, telling us when something's happened, or even better, I will see in my end of the presentation, that can take action of and decision of what is happening in our machinery. But if you go close look, this slide come from probably 10 years ago from ST Microelectronics. It's still the case that predictive maintenance, also intelligent maintenance, has a similar architecture. We have some robots, device, electrical motors, whatever can be monitored that need to be monitored with sensors. The sensors are producing data. These data are collected somehow from the sensor devices, or even better, from the physical devices to the cloud, or in general in some storages. And then the cloud mainly are extracting important information from this data. And then we can have a decision. We can go back to the people or to the user, or the people that are taking decision, or we can have automatic decision. And somehow we are giving a service to the monitored devices. This is still the case. So I think can change. You will see also already in my presentation, you will see some things completely different from wearables to robotics, but still we have this loop: devices, sensors, some intelligent software in the cloud or somewhere else, action that is some things they want to do to our machinery. And now I think also from the title of my presentation, there is a lot of interest and trends that are saying that AI, that this software I mentioned before, is more and more based on artificial intelligence algorithms that are not more than software or signal processing of this data, that are moving and are today used or performed in cloud. They are moved more and more on the edge. And this we are going to show what this means, because I would like to put all of you in what I believe and what I think is some things interesting, especially in the case of predictive maintenance and intelligent maintenance. So, but today we have the dominant part, and we are very happy of it, that we believe that with AI we can solve all our problems. I think especially the people from coming from the company, they are trust even more than us the fact that AI can solve the problem. Things that were problem before with this data, sensor data, they can be solved with AI. And this is true, actually, partially true. So I think we have a lot of problems that are solved, decision and information that this AI can give to us. And this is some things that more and more we are having in our vision and our products, that we are streaming information with a wireless connection or with wire connection from the device to the cloud to perform this very important, often a black box, but someone did this AI for you, so it's not really a black box for everybody, but somehow we have some software running there. And this means that we might have, I think, with this vision, very important information from the cloud, but also we need to pay, because this is the architecture, the technical details is coming from this picture. We need to pay the fact that we are transmitting information from the source of information, your device, to the cloud. This brings latency. We might have a data protection problem. Yes, your customer or your data are flowing to the cloud and you have no control of all the network to arrive there. You might have no wireless communication automatically. You need to send someone to control what is happening in your device because you don't have any more access to the data. And basically, you might have also the high power consumption. In some previous presentation, we heard about the sustainability, the fact that these cloud services are very, very expensive in terms of power. So these actually is the motivation are all there, and those are the features that moving the AI or in general the maintenance of the decision or the processing information, you can call in different way, close to where actually the things are happening in your device can bring benefit. Can bring benefit in latency. You can imagine that if you have a intelligent processing close to your sensor device that is connected to your machine to monitor it, you have a very high latency. Even if you are going toward the 6G, 7G, the latency you are paying to bring the data from that device to the cloud is in the range of milliseconds or even seconds. Let's say milliseconds. In the future, or in 5 years, we might have milliseconds. If you are performing your data analysis there, this become micro or nanoseconds. So it means that for particular application where your machine costs millions or billions, and you need to stop it when you detect the defect, this can be crucial. Because in milliseconds, you can break your machine, and in microseconds, you might save your machine. So it depends on application. But for sure, moving there, latency is one of the crucial aspects that we can have on bringing the AI there. Data protection, of course, you don't have any more the streaming. Still, someone can go there in your device to take the data, yes, of course, but still you are saving all the not control action for your company or for your system to stream the information there. You might even lead to some device. I think I like particularly the presentation of that they were explaining autonomous cars. You can basically have even not wireless communication. You still have intelligent device monitoring your systems. You go some remote area, you can have a problem. And of course, you can save power. This we'll see that is a problem. And it's a good point, but can be also your challenge. But in general, what more or less is agreed from everybody, that if we move the AI there, of course, we can have lower power, lower power, low latency system that can work in autonomy with a higher data protection and without communication. This will be very nice. But why we are still working there? There's magic in electronic informatics? No. We are working there for a single reason. That now we lack a lot of many different algorithms to process our information. We like a lot AI. We can say it's a black box. We don't know what is happening, but we are using it. Just an example also, ChatGPT, you can see that everyone is using it, even if it's in the cloud, even if we are transmitting our sensible data there. Why? Because there are big models that are performing well for our needs. You can correct your papers, or you can have idea, you can make a different kind of automatic intelligent research on it. But in general, this means that these models are really working to do it. So why we are not bringing this model and push back on this little course and edge? So the main reason is that today these models are quite big and large. So the other question can be that, so means that here I put there, so these models are so large that cannot fit an embedded processor. We are going to see what this means with the next plot. So what it means that even if you are called NVIDIA and you are able to do some things very impressive in terms of processing power, processor, you are paying it on the fact that all the processors are based on silicon transistors. So you are not special, you are NVIDIA and you are using different kind of technology. The transistor is the base of all the processors we are having, from our PC, our embedded system, our sensor with intelligence cores, and NVIDIA cores, NVIDIA platform. So why NVIDIA is so good? Because there are many people, but also because they are targeting data center systems. They are targeting processors that can work in the range of several watts. This is because we are saying cloud is very expensive. They are there. They are there doing AI, And that means that, of course, there is no magic. I mean, if you have a lot of power, you have a lot of memory, you have a lot of computational resources that in parallel can run your data. So is this enough to run all your models in mind for predictive maintenance? Probably yes. But what is the problem? The problem is that if you want to push at the edge, likely you will have a processor that need to consume less than a watts, let's say. You can have also few watts, but we are in range of watts versus different hundred of watts that we can spend. And as they are using the same technology, the same transistor, means that you are paying it in terms of memory and computational resources. So it means that if today you want to have the AI models that are very nice, are working in the cloud, you are very happy to do it, and you want to bring in AI, you cannot do it because nobody can go up this line. This is still the Moore law for the people who know electronics, that every 2 years we have double transistor with the same power. 2 years double. So you can already calculate how many years you need with your model very big there to put in an embedded system. This will be 20 years. Are you ready to do 20 years? Meantime, this model has changed. So what you can do with this compromise, because at the end you need to do compromise, is that somehow you can, this will be of course our target, having a larger model running in a low power, low cost processor. And this is a goal that is goal everyone that cannot jump the physics, means that to do it, at least our approach, but is approach to many people that are working more on the system view of bringing intelligence to the edge, are doing, and this is working to all the level, not only the high level to push performance, because we cannot push so much performance and receiving so much performance in low power way from the silicon, because this will not happen, because we need a fraction of, so we need 20 years to arrive there, but you can work at the system level. I will show it with some example on the low power design, on the machine learning. This today, my talk is not, I don't want to push too much machine learning on my group, but you can work on optimize machine learning for the power, the processor you are having, and change the sensor. You will see with practical example what this means. And also we work, this is something extra that I don't think I will have time to go through it. We work also in efficient communication that can lead to efficiency at system level. And more, this embedded system can be brought, this is what I'm going to show in the end of my presentation, to robotics that are not different than any embedded systems. And on this, I think just to give some overview, so I think it's these are the main 4 topics of my group that we work both in teaching and in research, supervising many students and PhD students as well. But I want to go more in concrete, because now this is an overview generic for my group, but in reality what this means. Means this, for example, that as we cannot create a new hardware platform that are doing processors, so GPU, for example, or microcontroller that are consuming few milliwatts or watts of power, but you can play on novel sensors. Not always is possible, but today there is a lot of interest and design of new sensors. This I put just an example that are producing relevant information for a particular application. This, for example, I don't know if starting, you can see that is the sample of an RGB camera in the middle versus a new event-based camera that is producing different way of data. So it means that, for example, if you are interested to see the movement of your hand, this camera can give you high latency in the range of 1,000 times more, let's say, equivalent frame, and reducing the data you need. You can see that you have a little spike in there, little data to process instead of the video that will need all the information, the pixel luminosity. So you can reduce it, you can go up of 1,000, 10,000, less data, and higher, lower latency in processing this data with some AGI, or in general efficient artificial intelligence, to do the same job. For example, in this case was a navigation system for a robotic platform using event-based camera. You can do the same job faster, a parity of technology in terms of CPU power, faster and with lower power. We are doing the same job with different sensor, different artificial intelligence. So we can push with existing hardware and existing solution in terms of hardware, software, bringing innovation on the combination to the level that are way more than the Moore law can give you, that is double memory, double computational resources every 2 years. You can go today some things in the range of 1,000 times lower energy, 1,000 times lower latency. And I think here there is a converter problem. So I think, as I mentioned in this talk, I'm not going too much to speak about also efficiency, but in this case, I want to show that, for example, this was using radar for gesture recognition instead of camera or other sensor. We could go down in this range of intelligence and the latency. We have all the gesture recognition with a little radar on earbuds, and we transmit only 1 byte, so efficiency only in communication, to the smartphone. Say this is gesture that the user, in this case our PhD student, was performing there. And then you will see that this architecture fit very well the application specific. Of course, this is valid only if you have clear in mind your application. Is this camera or any other sensor you will see in this presentation better than RGB camera? It's not true for everything. But if you want to identify this, because applications is important, a object, defect, or any other target where movement is very important, yes, this can be crucial bet. So, and you will see that actually it's often the combination of different sensors can bring the benefit. So this is because I think in our group in general, this in where you see energy efficient smart sensors in general, this is good to have application in mind to be covered and efficiency to all the level, from the sensor, for the low power design, for the AI part, and for the application eventually also the communication if this is needed. And I want to go through this example, so this topic with some example, why this can be crucial for many applications. This you can see that if you see only this node, this actually is a node that we did in cooperation with a company in Italy, that we were supposed to monitor temperature, humidity, and acceleration of the electrical machine. This is actually quite common, so probably you already saw it, that many people proposed that you can put a little node on your electrical machine, and then it's tell you, especially if it's at the cloud or sending information with the Bluetooth or energy, what is happening in your machine. And why with this we went a bit over this vision to get some things that it's self-sustained. So in this case, we would like to place the sensor there on the motor and don't touch anymore. So we want to place it with the right sensor and do it the alert only when something's happening. And to do it, you need to take energy somewhere. If you don't want the battery, you want to have the vision to have it working forever, you need to put a source of energy. In this case, we find the application very important, what was reliable there. So we have a difference of gradient. So we have the motor that we can rely on the temperature around 50 degrees and the airflow that is 25 degrees. So we could exploit the thermal energy harvesting. So why this is important? First, low power design. Second, we can take energy for what is available. So if you tell me we work with vibration here, we don't have enough vibration. So this was an example. Second, after we know how much power we are having, we need to design the node to have on-device processing. We did the opposite. Before we see energy, then we decide, then we set up our processor power. This was a processor that could not consume in average more than microwatts of power. And if we combine all together, including the tiny machine learning that is able to perform the condition and the prediction of the condition of the machine, we can have that in normal condition, we have with the battery 5 years of life. In reality, we can have a self-sustaining system that can be placed, like you can see in this case. I think now this probably became a product from the company. We are working together, and basically you can monitor your machine in different way. Of course, this is a completely flexible, custom system, then you can tune for your specific goal. And this is also what we did. So I think with the same approach, we were working with the different intelligence sensor nodes. So they are using something similar. So a Bluetooth Low Energy, ARM Cortex M4 core, so little microcontroller consuming a range of milliwatts of power. And we could retuning it, changing of course the shape, changing the sensor according. So here we see many sensors we are using for what is doing it. Why this vision could be interesting? Because this actually is a slide coming from ST Microelectronics that is launching, and actually we are working with them to launch it, a new new branch of sensors that have on-device core inside the sensor. If you just come from, let's say, from the users of the sensor, say how this can be. And there is no magic also there. They just integrate a small core with the same technology transistor, digital transistor, to do AI feature. So it's a small microprocessor inserted inside the same package. Why this could be very interesting? Because this is very interesting for cost reason, for space reason, for supply reason, because it's consuming microwatt of power, and to have an always-on system that can monitor your machines. And this is because I think this approach is important, because as you didn't go in detail of artificial intelligence, we were using only some kilobytes of memory to perform our AI part. And it's actually a system that has more or less 16 kilobytes free to do it. So actually our model can already run on it. And of course, there is trade-offs to do it. So this is some things that is happening. It's not only ST Microelectronics, Analog Device, Bosch are proposing something similar. And just to continue with the use case, and then I go to the conclusion, this is an approach that you can use in different ways. So these are all projects that we are using in our system. So in this case, we were doing a project for wind turbine monitoring, where ice is important. Also, the aerodynamics is very important. And we start from scratch. We didn't know, actually, also the expert didn't know very well what to be monitored. And actually, this system will monitor everything. So they were using very expensive on the wind turbine tunnel, very expensive sensor node in all the blades to see what can happen. And this is also come from the design optimization. So we really basically design, again, the differential pressure sensor, a monitoring system, pressure sensor, vibration, and also we try different other sensors are not displayed here. And really we checked what is the best solution and the best position of the system to make again, this combination of sensor acquisition and AI to make the best detection for both ice monitoring and also the demand flow. And this also, it's a startup that went out after this research project that are trying now to get more in-field demonstration, but all the hardware, software, and the firmware and the main machine learning part was done to us. And just I'm giving a bit fast here because I want to go to the robotic part. So we did also some cooperation with SBB, where we wanted to investigate how we can have IoT nodes, ultra low power and self-sustaining or battery operated to have to monitor the integrity of the train, especially for the cargo that are not today supplied by the different sensors. And with the same approach, we end up with the ultra wideband technology that was able to get, you will see with the video better. So you can have two different nodes, and these nodes are coordinating each other. You can see that the blue line there, I think when the train is coming closer, 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 you can monitor in real time what is happening, where is the distance on next cargo. And then basically you can use this information to see if your integrity is still there. And I want to, again, close the loop with the robots, because today this is a big reality. I don't know if you hear about the introduction talks or many talks NVIDIA person has. They are not pushing anymore on doing a new platform. Of course, they're doing new platform, but their goal is not having people doing AI models. Their goal is doing the physical AI. So bring AI on the physical world. So it's an embedded system. And why? Because they have even more consumer. It's not only people in the PC that are sending their text to send back, but they can bring intelligence where it's needed on the field. And in a particular way, on the intelligent predictive, intelligent maintenance or predictive maintenance, the approach is very similar. So what we are working today, I'm coming from the wireless sensor network, we are moving now or robotic, but we are the same person, because the option there and the important field there are the same. Edge computing, we want to bring AI in a small embedded platform. Also, the embedded platform of NVIDIA is consuming 10 watts, not millions of watts. You need to combine it with a system that can work without wireless connection. You have sensor fusion algorithms. You can have the efficient algorithm need to run in this algorithm in this platform, and you can also lead to cooperation. And I want to close it with two little examples. So I think we did a lot of investigation on different sensor radar, and we use this little platform that is a little robotic platform to show that if you change the LiDAR, it's today used for autonomous driving, and it's used for many autonomous systems. A LiDAR is expensive, 3,000 euro for a LiDAR, and you need a big platform to process the information. You can work with these 3 sensors that cost $1, $1, $1 to get to have a SLAM system. So I will show it with a video. You can have a SLAM system. This is a small drone. We use a small drone for a single reason. We want to do a stream in a challenging scenario. There are a little combination between little time of flight sensor from ST microelectronics, radars, and ultra wideband to coordinate them. You can have 4 little drones that are able to make a SLAM map that are known system without knowing everything. There is no connection with the cloud, no connection to the vehicle room, no connection to anything. There are only the 4 drones coordinated by them, and this system can run in a microcontroller that consumes 10 milliwatts of power. No GPU, no NVIDIA. Of course, we work also with the bigger things, and here I don't have time to go in all of them. These are the sample of this event-based camera, and we try to build our own hardware software system. We are electrical engineering by nature, so we work with hardware and software. The robotic we buy like a toy. We can use even a Ferrari down, but we build our own system with a novel sensor, a novel architecture in terms of performance platform. In this case, we are using mainly the GPU from NVIDIA target. In this case, we can have even further investigation of different kind of monitoring. In this case, we were investigating, we're still investigating a European project with the crack detection, with the depth camera, even base camera. And I think my time is closed. And I think these are more or less a sample of this robot that is a big waves and what we are doing also in terms of configuration between the wearable device and robotics platform. I'm slower than my normal, but in general, what I want to show is that I think I strongly believe with the novel sensor fusion, and the combination of sensor, AGI, and application, we can cover a new branch of application. With this, I think I can close with a video that is going just alone to show that these things are really working to make a combination of different monitoring systems that are mobile and small, like the small drone that you are having. Thank you very much, and I think the discussion come after. Thank you.